So in the last session, we covered this cutting forces, the relationship between them, then velocities in the cutting zone, and we were about to begin with this orthogonal versus oblique cutting. Now, before getting into the concept, I'll ask you one simple question that you might have observed in your daily life. The question is, suppose uh, you are at your place in your home and you are helping out your mother, and what task has been assigned to you? You need to cut the tomato with a knife. So two scenarios you are going to follow. The first one, while cutting the tomato, you need to hold knife perfectly straight or exactly vertical, and you need to try to cut that tomato. That is the first scenario. And in second scenario, what we need to do, instead of holding that knife exactly vertical, you are going to tilt it at certain inclination with the vertical. Okay. And now in that scenario, you need to try to cut the tomato. Suppose that situation is situation B. Now, few students from you might have observed that in one of the situation, you need to apply more force, and in one of the situation you need to apply less force. So can you tell me in which scenario you will have to apply more force, and in which scenario that force requirement will be slightly on the lower side compared to other one? Situation is situation A and situation B. Unmute and let me know, or you can put it in chat window also. In which scenario the force requirement will be more, A or B? Okay, Akash. Okay, Vaibhav. Anybody else? Manoj. Okay. Okay. So all of you have got the right thing. So the thing is, in case of situation A, the force requirement is going to be more, whereas in case B, the force requirement is going to be less. This one is known to us, right? Or this one we have observed. We don't know the scientific reason behind this one, but we are following this one, right? So out of those scenario, the scenario A is called as orthogonal cutting, and scenario B is called as oblique cutting. Okay. Now let's differentiate those two things in a details. So the first figure A indicates a orthogonal cutting and B indicates a oblique cutting. So what is the difference between those two? The difference is this is our cutting tool. This is going to move in this direction, removing this much layer, converting it into a chip. So tool is going to move in this direction and it is going to remove the material. Now while moving in this direction, if you observe the orientation of that cutting tool, this is the cutting edge of that tool. Okay. And that cutting edge and this is the direction in which that cutting tool is going to move, or that is direction of motion. Now if you correlate the cutting edge orientation with the direction of cutting tool motion, those two are perpendicular to each other. Okay, that's case one, or that is orthogonal cutting. Whereas in case of oblique cutting, that cutting edge, instead of being at a right angle to the direction of motion, now that would be tilted slightly. So that's what you observe over here. Actually, if I draw a line like this one, these two are parallel to each other. And if you look at the cutting edge, that is making some angle with that also, right? So in this scenario, the cutting edge is not perpendicular to direction of motion, but it is now inclined at certain angle with the direction of motion. So this second scenario is called as oblique cutting. Okay. Now that is the basic difference. Now few additional differences comes into picture because of this cutting tool edge orientation. What are the additional differences? Now, in case of orthogonal cutting, there we need to consider only two cutting forces. What are those two cutting forces? The cutting tool is moving in this direction. So there will be one force acting in the direction of motion, and that force is cutting force Fc. And there will be one another force that would be perpendicular to this cutting force, and that force is called as thrust force Ft. So only those two forces we need to consider in case of orthogonal cutting. Usually you will find a resultant of those two calculated and represented somewhat like this. But that is not an additional force, that is resultant of this Fc and Ft, that is cutting force and thrust force. So here you will get that Fc cutting force, Ft thrust force, and resultant of those two. Whereas in case of oblique cutting, in addition to that thrust force and cutting force, there will be one additional force comes into picture, and that force is called as a radial force, because that cutting edge is now at certain inclination. Because of that one additional force comes into picture, that force is called as a radial force. So in case of orthogonal cutting, there are two forces. In case of oblique cutting, there are three forces. Now, when I try to represent this force system, I will have to take a help of only two axes, because one force I will represent on this axis, one force I will represent on this axis. So the representation system will be a 2D system. Whereas in case of uh, okay, I wrote it on the wrong place. Actually, this is orthogonal cutting and this is oblique cutting. Okay, so this one I should have written over here. So this is 3-4 system and this is 2-4 system. So the thing that we need to consider is, in case of orthogonal cutting, there would be only two forces that you can represent using two axes, and you will get a 2D system. Whereas when it comes to representing forces in case of oblique cutting, there are three forces. So along with x and y, we need to take a help of third force. So now this becomes a 3D system, because there is now third dimension that has come into a picture. So this oblique cutting is also called as 3D cutting. Why it is called as 3D cutting? There might be a multiple choice based question on this one. Why do we call oblique cutting as 3D cutting? The answer is because there is an involvement of three cutting forces, and to represent those three forces we'll have to take a help of three axes simultaneously. That becomes a 3D system, and that's why this is called as 3D cutting. Now another difference is that difference you can easily understand in case of oblique cutting, orthogonal cutting. There are two forces. In oblique cutting there are three forces. So when I try to analyze the force system, it is but obvious that orthogonal cutting I can analyze easily because only two forces are there. Whereas in case of oblique cutting, there is one additional force that is going to make a system little bit more complicated compared to orthogonal cutting, and analyzing that system will be difficult one. And because of these things, whatever metal cutting theories that we are going to study, those theories are based on this orthogonal cutting only. Okay, the reason is only two forces we need to consider. These systems are simple to analyze. We need not to go for multiple assumptions that are going to complicate the system. Okay, because of that one, the metal cutting theories are based on orthogonal cutting that we are going to study. So that is the difference between orthogonal cutting and oblique cutting. If you have any doubt, any query, let me know. Okay. So additionally, when you compare this orthogonal cutting and oblique cutting, from the sketch itself, you can get that the cutting tool is moving in this direction. On formation, chip is going to flow across the face of the cutting tool. So chips are going to move across the face of the cutting tool. Whereas in case of oblique cutting, what will happen? Once the chip has formed, it will try to shift in this direction. So chips will flow like this one and not like uh, across the cutting tool face. So if you compare the flow of chips in orthogonal and oblique cutting, in case of orthogonal cutting, the chips flow over the tool, while in case of oblique cutting, the chips flows sideways. That is the another difference. Now last difference, the uh, as I said, in case of orthogonal cutting two forces are there, in oblique cutting three forces are there. Additionally, if you compare the magnitude of forces, the major force that is responsible for the chip formation, that force is nothing but the shear force. If you compare the magnitude of that shear force in case of orthogonal cutting, that shear force is going to have more value compared to oblique cutting. That we know, right? When you try to cut that tomato with a knife holding it exactly vertical, we were required to apply more force, right? So the magnitude of this shear force in case of orthogonal cutting is more compared to oblique cutting. So these are the differences that we need to consider when it comes to differentiate the orthogonal and oblique cutting. Any doubt, any query? What are the point you need to remember? The cutting edge orientation, perpendicular to the direction, inclined to the direction, two forces, three forces, 2D system, 3D system. It is easy to analyze, it is difficult to analyze. The chips flow across the face, chip flows sideways. And last one, shear force is going to more in case of orthogonal cutting, and shear force is going to less in case of oblique cutting. So those are the differences that we need to consider. Next, cutting forces and power. Now we have studied few forces, the majorly cutting force, thrust force. Also, we talked about shear force. In addition to these forces, when you want to analyze a material removal process, there are few additional forces that we need to consider. Out of those forces, few forces you can measure directly, and few forces you need to calculate from the forces that you have already measured. There will be certain relationship between the forces, and if you have measured few forces, you can use those measured forces to calculate the remaining forces. Okay, so what are those forces? Before uh, talking about those forces, let's talk about the importance of knowing the forces. Why do we need to study the forces? Or having an idea about the forces that are supposed to generate while metal cutting. Why do we need to uh, uh, have better understanding of those forces? This concept we have discussed already while talking about the abrasive machining. Why we need to consider cutting forces, or having knowledge of cutting forces is important? Why? The first thing is, the machine tool can be properly designed to minimize the distortion of machine component. So we know that during the metal cutting, the forces are going to generate, and the magnitude of those forces should not be large enough to distort the machine tool itself. So there is cutting tool, there is workpiece mounted in the chuck, it is being rotated, the work cutting tool is provided with these two motions, cutting motion and feed motion. Now, when these two things, this workpiece and cutting tool, are going to have relative motion against each other, there are forces that are going to be exerted on the parts that are going to support the workpiece and cutting tool. So these supporting parts are supposed to rigid enough to support the forces are to be generated. If these parts are not rigid enough to support these forces, what will happen? The machine tool itself will start distorting, and that is not desirable. Because what will happen? If that distortion is there, you will get the second thing. What will happen? The dimensional accuracy that we are expecting from that machine tool, that will not be achievable. Why? Because whatever reference positions that I have considered while beginning with the metal cutting, because of distortion, those reference things are not fixed now, because machine tool itself has got distorted. So the reference points might have shifted backward, right, left, in any direction, right? And now the workpiece dimensions are going to be affected by that distortion. So it is obvious that the accuracy or dimensions that I'm expecting from the workpiece will never be achieved. Okay, so that will be the second thing. Now, third, The workpiece is capable of withstanding these forces without excessive distortion. Now, this thing comes into picture when, suppose this is a headstock, this is a tailstock, somewhere here there is tool holder, and you are going to machine a component whose, or if you compare the three dimensions, width, thickness or height, and length of that component. So three dimensions. Out of those three dimensions, if width and thickness is very small and length is very large, such a kind of workpieces are called as slender workpieces. Now what happens in case of machining of these kind of slender workpieces, if I try to have some operation somewhere at the middle, so what will happen? Its thickness and width is very small, whereas its length is very large. When I try to have some operation somewhere here, the chances are that the workpiece might get bent across this point because it is slender one, right? So in machining of such a workpieces, I need to have better idea of magnitude of forces to be generated, so that I will get to know whether this workpiece is capable of withstanding those forces. And once I have that idea whether that workpiece will be capable of withstanding those forces, then I'll continue with the machining. If not possible, I'll have to think of some alternative, right? So that is the another thing that is that makes necessary understanding the cutting forces. And last one, power requirement. When you want to remove the material, we need to provide a relative motion. The workpiece has to be rotated, the cutting tool has to be provided with these two motions. And to provide these motions, I need to use some electric drives or some kind of drive we need to provide to have this relative motion. And selection of those drives will be dependent of the magnitude of forces. Larger the forces, the electric or the drive capacity has to be large enough. If the forces generated are very small, I need not to go for those large drives, because that will unnecessarily increase the energy consumption. So I can work with the small drives also. So accordingly, once I have a better idea of the forces, these requirements will be fulfilled. Any doubt, any query? Okay. So next, a merchant's theory. As I said, we are going to talk about few theories that will be helpful in the measurement and calculation of the cutting forces that are going to be generated while having the single point cutting tool, metal cutting. So out of those two theories, the first theory is called as merchant theory. Now what happens in case of merchant theory? Let's begin with this basic sketch. This is a single point cutting tool. This is going to move in this direction. This is the workpiece surface and this is the chip width. The chip is going to be generated and move across the cutting tool face. Now cutting tool moves in this direction, removing the workpiece material in the form of chips. There are two major forces acting on the cutting tool. This is orthogonal cutting. So two forces. The first one is cutting force that will be acting in the direction of motion, and another will be a thrust force that would be perpendicular to the direction of cutting. Those two forces are there, and this is a resultant of those two, Fc and Ft. When you calculate the resultant of those two, it will lie somewhere here. Okay, so now these two forces, suppose I have measured. Now with the help of those two forces, if I want to calculate some additional forces that are necessary in analysis of metal removal process, I will use merchant theory. So what we do in case of merchant theory, let me erase this one. Refer this figure. So this is cutting tool moving with velocity in this direction. This is chip flowing in this direction. If I draw a perpendicular over here, this is going to be angle alpha, that is rake angle. This is the shear plane, along with material is going to shear and move across the tool face. The inclination of that shear plane will be denoted by angle phi. Okay, those two angles are known to us. Now additionally, when you want to calculate the remaining forces, instead of using this one, let me draw it. So this is cutting tool, this is shear plane, this is chip form, this is depth of cut T0, this is chip thickness TC, and suppose this is the finished surface and this is uncut material. So this is our tool. Okay, so this angle is phi. Across this face, this is cutting force Fc, and perpendicular to that one there would be one force acting perpendicular to cutting direction, that is called as thrust force. Now instead of drawing this thrust force over here, what I'll do, I will draw that thrust force over here. Okay, so this is Ft. Now if I calculate a resultant of those two, it will lie somewhere here. Now what I need to do, I will consider this resultant as a diameter. I will locate midpoint and I will draw one circle. What I did, this is cutting force, this is thrust force, those two are perpendicular to each other. I calculated resultant of those two, and taking that resultant as a diameter, I I have drawn one circle, and when I drawn that circle, the point where this FC and R meets, where that FC and FT meets, and where that R and FT meets, all are going to lie on circumference of that circle. Okay, so this is one thing. Additionally, let me change the ink. This is shear force Fs. If I draw a perpendicular to this shear force, that will appear like this one. So this is Fn. So this is shear force and Fn is normal shear force. And again, if I calculate a resultant of those two, it will appear like this one only. Okay. And now again, what I'll do, I will take that resultant as a diameter. We'll locate its midpoint and we'll draw a circle. So what will happen? That circle will appear like this one, and this point, and this point where two forces are meeting each other will lie on the circumference of the circle. That is the second case. Now, third case, the formed chip is going to flow across the cutting tool face in this direction. So when it moves across this cutting tool face, there will be some friction between the chip and cutting tool. So chip is moving in this direction. So there will be a frictional force F acting in this direction. If I draw perpendicular to that one, this will be a normal force. And what I will do, I will calculate a resultant of those two. So it will appear like this one. And if I calculate this angle, that will be a friction angle that is denoted by beta. This is frictional force, this is normal, and we know that beta or friction angle is F by N. Okay, so that way you can calculate the friction angle. Now, instead of drawing it over here, what I will do, I will shift it in the downward direction. So this frictional force, I want to change the color, but I'm not able to. Yes. So this is frictional force. Instead of drawing it over here, I have shifted it in this direction. So this is our frictional force. From here, I will draw one perpendicular to that force, just like this normal. So now this is my normal. And when I calculate resultant of those two, again this will appear like this R. That is the resultant. And again I will locate its midpoint and will draw a circle. So what will happen? Again this point, this point, this point that I have drawn in this direction. So this point and this point will lie on the circumference of the circle. Okay, so we considered three scenarios. Now let's combine all those scenarios together. In the last lecture, we were taking a look of this merchant's theory. Before that, okay, let me continue. Yes, so suppose there is a single point cutting tool. This is material being cut with chip. Suppose this is a depth of cut T0, and this is uncut material where this is the finished surface. So there are two major component of forces. One acts parallel to the direction of motion. That force we call cutting force Fc, and there would be one more component that is going to be perpendicular to the direction of motion, and that we call thrust force Ft. Okay, and when you calculate resultant of those two, that resultant will lie somewhere here, and that is going to be a replacement of that cutting force and thrust force. After that, what we saw next, So I'll draw few more sketches over here. So this is a cutting. Okay. So in this sketch, if I consider this as a cutting force Fc, instead of drawing that thrust force over here, I will draw over here. This is our thrust force Ft. And if I calculate a resultant of those two, so resultant will lie somewhere here. Now what I need to do, I will take this resultant as a diameter of circle, will look at the midpoint and will construct one circle. So what will happen? All the endpoints of the forces will lie on the circumference of the circle. So this we done for the Fc and Ft. Additionally, I will draw one more sketch. Again, this is a cutting tool. This is chip form, finished surface, uncut surface. Okay. Now here we know that material shears along this plane. The chips are formed parallel to this plane. So this plane is called as shear plane, and one component of force lie along that plane. So suppose that component is shear force Fs that will lie along the shear plane. Now I will draw one component that would be perpendicular to this shear force, and that one is called as normal shear force or normal component of that shear force. Now again I will calculate a resultant of those two. It will lie somewhere here. I will look at midpoint of that resultant and will construct a circle. So again the forces that I have considered over here, Fs and Fn, their endpoints are to lie on the circumference of the circle. So this is second case. Third one, again, okay, no, I'll draw it over here. So this is a single point cutting tool, cheap, finished surface, and uncut surface. Okay. So now what happens when this chip moves in this direction along this rake face of the cutting tool, somewhere here there will be a friction between chip and the rake face. So chip is moving in this direction, so opposite to that there will be a frictional force acting along the rake face of the tool. Now similar to this normal component of shear force, I will draw one component over here that would be perpendicular to this frictional force, and let's call that as a normal reaction of the frictional force. So similar to previous two cases, again I will mark the resultant of that F and N, and it will lie along this plane. So this is a resultant. Now instead of drawing it over here, what I'll do, I will draw this frictional force. So instead of putting it over here, I have shifted it downward. Direction is same, so I can relocate that force, right? That is the principle of transmissibility that you need to look into the engineering mechanics. So I have drawn frictional force over here. Now I will draw this normal component in this direction. That would be perpendicular to frictional force. Okay, and now I will calculate resultant of this F and N and again that will lie in this position. So I will locate its midpoint and draw one circle. So again, all the forces will lie on the circumference of the circle. So this one we did for frictional force F and its normal N. So now we have seen six forces individually. So now what we need to do? I need to combine this figure with this one with this one. So these three figures we need to combine. So what we will get? Anybody has got any doubt in this one? Whatever I have drawn on the screen. If you have any query, let me know so that I would explain it. Once I switch to that PPT, this whole thing will be vanished. So if you have any doubt, any query, let me know. Okay, I'll take that as nobody has any doubt, any query. Okay, so when you combine these three figures, you will get this one. So how we have combined? This is our cutting force FC. This is thrust force FT, a resultant of those two. Okay. Then shear force Fs, normal component of shear force Fn, and resultant of those two, again same resultant component. Then frictional force F, perpendicular to that normal reaction component of that frictional force, and again a resultant of those two will lie along same resultant that we have drawn. So now this resultant is common for those six forces. Okay, and if I locate its center and draw one circle, all the six forces are going to lie on circumference of this circle, and this circle is called as merchant circle. Okay, now once you have got the sketch, there are certain angles that you will get from the basics that we have seen till now, and some angles we need to calculate. So let's see how we can do that. So this angle is alpha. How we get that alpha? This is a cutting tool, a cheap finished surface, unfinished surface. So when I draw a perpendicular over here, the inclination of rake face with that perpendicular is alpha. Okay. Now I have drawn a frictional force along the rake face, and same force I have extended in this direction. So this is my F now, this F. And if I take inclination of that one with vertical, actually this is the same line that I have extended, and this vertical also same line. So if this is alpha, this also becomes alpha. Okay, so that's how this is a rake angle alpha. Then this total angle beta, this angle is called as friction angle. Now how we get that friction angle? Let me change the ink. So this is a frictional force F. We draw one normal to that frictional force N. Now if I draw resultant of those two, suppose this is the resultant of this F and N, this angle, this is 90. Okay, and this angle I need to find. Then if I take tan of that angle, if this angle, if I call this as beta, and if I take tan of beta, that will be opposite side, that is F upon adjacent side N. So that will be F by N. Okay, that you can calculate. And by similarity of triangle, if this is beta, same triangle we have extended over here. So this angle is nothing but this opposite angle. This 90 degree is this 90 degree. So what left with us? This beta. So this angle is also beta, and that is a friction angle. So we got alpha, we got beta also. Now this phi is shear angle. That is, we are very much familiar to that one, right? This is a cutting tool, chip flows along this direction, and this is the shear plane along with the material shears. And inclination of that shear plane is nothing but the phi, denoted by or called as shear angle. So this alpha is known, phi is known, beta is known. Now let's calculate the remaining angle. Suppose this angle to be calculated. Okay. Now this total angle is 90 because this is vertical and this is horizontal. Okay. Out of that, this one is known alpha, and those remaining angles we need to calculate. So how will we calculate that one? Total 90 minus this is 90, this is beta. So in this triangle this angle will become 90 minus beta, because this is 90 and this is beta. So 90 minus beta, and what left with us? This one. So suppose that angle is, let's call it as a, or that we need to calculate, right? The angle 90. Okay, I forgot to take this alpha also. So total 90, from that one we subtracted this 90 minus beta. We need to subtract this alpha also. So that will be 90 minus alpha, and remaining angle will be this one. Suppose we call it as A. So now let's solve this bracket. So 90 minus 90 plus beta minus alpha is equal to A. This 90 will get cancelled, and we will get beta minus alpha is equal to A. So we have got this beta minus alpha. Now last one, this alpha. Now this is a horizontal, this is horizontal. Okay. So if this is beta minus alpha, this angle is also supposed to be beta minus alpha. And we know that this total is beta, so remaining will be alpha. So that's how we get this angle alpha, that is inclination of normal with the horizontal. So now once you have all the inclinations and magnitude of few forces, you can construct this circle and calculate whichever force has been asked to calculate, whether it is thrust force, normal component of shear force, cutting force, frictional force, or a resultant of all those forces. Okay. So you just need to use the trigonometry, because in this triangle this is 90 degree, so it is right angle triangle. In this triangle this angle is 90, so again this is right angle triangle. And in this triangle this is 90 degree, so again it is a right angle triangle. So you can apply that sine, cos, tan, all relations in all these triangles, and you can get any force. Okay, that is the use of this merchant theory. So these are the relations that you can get from the that triangles by applying trigonometry. So we are not going to take a look of these relations that you can easily get. Okay. Now next important thing that we need to discuss about the thrust force. Now in this case, we know that when metal cutting, or when you consider orthogonal cutting, the two major component of forces are cutting force and thrust force. Okay, this Fr is the resultant of those two that you have calculated, but the two major forces are cutting force and thrust force. Now when you compare the magnitudes of those two, this Fc is always going to have some positive value. Why this Fc is going to have positive value? Because this cutting force provides all the necessary energy for the formation of chip, and as long as material removal is being takes place, this Fc is always going to have non-zero value. Whoever is talking in between, mute yourself. Okay, so out of this Fc and Ft, this Fc is always going to have positive value, but when it comes to this Ft, that is thrust force, it could be positive as well as negative. When we say it is positive, it acts downward, and when we say it negative, it acts upward. Now why this could be positive as well as negative? Now, if you look at the relation for that thrust force from the merchant circle, when you apply trigonometry, you will get Ft is equal to R sine beta minus alpha, or Fc tan beta minus alpha. Now, in both the relation, the magnitude or sign of this Ft will be dependent of this beta and alpha. When beta is greater than alpha, this Ft will be positive, and when beta is smaller than alpha, this Ft will be negative. Okay, so thrust force could be positive or negative, or it could act downward as well as upward, depending upon the difference between this beta and alpha. Beta is our friction angle, and alpha is the rake angle. Okay. Next, Lee Shaffer theory, the merchant theory, and another theory that we are going to take a look of. In short, is the Lee Shaffer theory. Now, while taking look of merchant theory, the one assumption that we made was the chip was considered to be a rigid body that is hold in equilibrium against all the forces acting or generating during the metal cutting. Okay, so chip was considered to be a rigid body. Now when it comes to Lee Shaffer theory, the assumption is, instead of considering a rigid body, now the material is considered as rigid plastic. Now, what is mean by rigid plastic? When you apply force to a material till yield point. Yield point means a point up to which or beyond which, when you apply force to that material, material will deform plastically. Okay, so up to or beyond yield point, the material starts deforming plastically, and because of that reason, we apply plasticity theory. Again, Lee Shaffer theory is also going to be based on orthogonal cutting only, because we know that if you compare oblique and orthogonal cutting, this orthogonal cutting is simple, involves less forces, you can easily analyze it, and because of those reasons, this plasticity theory will be applied to orthogonal cutting to analyze the force system. Now there are certain assumptions that we need to look uh, that are important in case of this Lee Shaffer theory. The assumptions are: first one, the material is a rigid plastic. Now, what is mean by that rigid plastic? Rigid plastic means the elastic strain is negligible during the deformation, and once that yield point is exceeded, deformation takes place at constant stress. So the first assumption is the elastic strain. Elastic strain means the change in dimension to the original dimension till the elastic point. Okay, till that point, the elastic strain is negligible because we are applying plasticity theory. So we need not to worry about the things that happens during the elastic limit. Okay, and after that yield point, the deformation takes place at constant stress. So after that, the stress is supposed to remain constant. Now the second assumption, the behavior of material is independent of the rate of deformation. So whether that deformation rate is increasing, decreasing, or it is fluctuating in nature, irrespective of that, the material uh, properties or behavior of that material is going to remain constant. That is the another assumption. Now the third assumption, the effect of temperature increase during deformation is neglected. Now we know that if temperature increases, it has got adverse effect on the material. There might be softening of the cutting tool, softening of the workpiece, and once that material has got softened, the properties are going to change, right? But what we are assuming that the effect of temperature increase during deformation is neglected. So that is the third assumption. And fourth one, the inertia effect. Now how what is this inertia effect? We know that while removing the material, if this is a cutting tool that forms the chips and then chips flows along the cutting tool rake face. Now when those chips forms and moves in this direction, that chips might have some inertia force associated with it. And to simplify this analysis, we are going to neglect the inertia effect as well. So all these are the assumptions. With all these assumptions, we are going to apply this one to again orthogonal cutting and analyze the forces. This theory need not to be studied in detail. You won't find in that regular book that we are going to refer, that is uh, Manufacturing Science and Technology by Kalpak JM. You will not find anything else beyond these assumptions. So just remember these assumptions that there might be a multiple choice questions based on these assumptions only. Okay. Next, power and specific cutting energy. Now, the specific cutting energy term we have discussed in abrasive machining, but we'll apply that to this single point cutting tool also, or single point cutting tool machining also. Before that, what is mean by power? So the power is actually the total amount of energy that is being consumed in total amount of material to be removed. So it is not actually rate, ratio, or something like that. It is just suppose I have removed certain amount of material from the work surface. What amount of energy I have consumed to remove that material, that amount of energy is nothing but the power required. So it is a product of cutting force and cutting speed. Fc into V. V is the cutting speed and Fc is the cutting force. If you take product of those two, you will get the power. So now suppose I have total amount of energy consumed in the material removal, and I have total metal or material removed also. Now by using those two, I need to write the relation for specific cutting energy. Now we know that specific cutting energy is the energy required to remove unit volume of material, that we know, right? When you want to remove unit volume of material from the work surface, the energy required is nothing but the specific cutting energy. Now, to calculate the specific cutting energy, what we need to do, this specific cutting energy PS is equal to PM. PM is the power or total energy consumed. When I divide that power or total energy consumed by material removal rate ZW, ZW is the material removal rate. So I know what is total amount of consumed and I know the material removal rate. If I take ratio of those two, I will get the energy required to remove unit volume of material. So that is nothing but the specific cutting energy. Now there is one alternative relation to calculate this specific cutting energy itself. The alternative relation is FC by AC. FC is the cutting force and AC is cross sectional area of uncut chip. Now what is that cross sectional area of uncut chip? This is a cutting tool, this is finished surface, and this is uncut surface. Now this is uncut chip thickness T0. Now when this tool moves in this direction to remove the material, this is one dimension. Now depending upon the width of the tool or cutting edge of the tool, this chip is going to have some width associated with it. And when you take product of that width with this uncut chip thickness, you will get cross sectional area of that uncut chip, and that is denoted by AC. So when you take a ratio of this AC with cutting force FC, that you will get this specific cutting energy. Okay. Next, flowing force and size effect. Now, before discussing the size effect and all, can any one of you let me know what is mean by flowing force? This thing we have discussed in maybe second or third lecture. So can any one of you tell me what is this flowing force? Unmute and let me know, or you can put it in a chat window also. But if putting in chat window, you need to write the definition. So better you unmute and let me know. What is this flowing force? Yes, I'm still waiting for the answer. आकाश सांगता येईल? आहे का आकाश? Yes. Akash, can you tell me what is this flowing force? While talking about the specific cutting energy, in abrasive machining, we discussed that this specific cutting energy will be utilized for three things. What are those three things? First one is chip formation. Second one is flowing force. And third one is friction. So these three phenomena are going to consume this specific energy or specific cutting energy. So chip formation you can get Friction is the friction between cutting tool and work surface, and third one is flowing force. So what is that flowing force? Flowing force is when cutting tool moves in this direction by removing material or converting that material into chip. What happens before this chip separates from work surface? The chips gets accumulating in front of this cutting tool. There would be a certain accumulation of chips in front of the cutting tool, and when cutting tool moves ahead, the cutting tool is supposed to push this material along with it, and that pushing action is nothing but the flowing, and force involved in that phenomena is nothing but the flowing force. Okay, I hope everyone will remember this one now. So this flowing force and size effect. So what this concept is? So this is a cutting tool. Okay. Now this cutting tool is going to be in a contact with workpiece or workpiece material at three locations. What are those three locations? First one over here, where the cutting point or cutting edge of the work cutting tool comes in contact with the workpiece, and where actual chip formation takes place or material removal takes place. That is the first location. Second, when chips are formed and chips are moving in this direction across the rake face of the cutting tool, the chips will be in contact with cutting tool over here, and that region is called as chip tool interface. That is the second region. Third one, now we expect that cutting tool should have a pointed nose. It should be a, or it is expected to be perfectly sharp all the time. But this is a small corner point, and if you start machining with this cutting tool, the first point to be worn out is this cutting edge. Okay, and in most of the cases, after machining for a certain duration, this will worn out slightly, and because of that one, what will happen? The surface of the cutting tool will start rubbing with the finished work surface. That is not expected, but it happens all the time. There will be a certain portion of cutting tool that will be in a contact with finished work surface. So that is the third zone. So what are the three zones? First one, a cutting edge coming in contact with the workpiece where actual material removal takes place. The chips flows across the cutting tool rake face. So that is chip tool interface. And the third one is work tool interface that comes into existence once that cutting edge of the cutting tool has worn out slightly, and because of that one, this third zone comes into picture.